Hello and welcome. In this video we're going to take a look at slope fields. So slope fields are another qualitative method that allow us to visualize and understand better what's happening to the solution of a differential equation. So slope field is exactly what it sounds like. It's a field or a space filled up with slope vectors. So one of the things that we know, if we can't solve a differential equation, or the differential equation might be too hard to solve, or we just kind of want to get a sense of how the solution behaves, we can really take advantage of what dy dt is. So dy dt, this symbol represents a slope, and we know that out of any given differential equation, the input is, or the inputs can be t and or y, and the output is a slope. So geometrically, a slope can be visualized by a line segment that has a steep or not so steep incline, or a steep decline, or not so steep decline, or anywhere in between, of course. And so every time we generate a slope for a given input, we can, at that ordered pair on the ty graph, sketch a small vector that represents the slope at that point. Let's go ahead and take a look at this very first example that we have here. So we have a slope, we have a differential equation, and we want to sketch a slope field for t over the interval 0 to 2 and y over the interval from -1 to 1 at each of the integer points in this region. So of course the reason we're saying this is because there are infinitely many points, even from t equals 0 to 2. So if on this graph I label this as t equals 1 and t equals 2, and then y goes from -1 to +1. So we are only focused on values on these four integer points, but we'll have a point here, a point here, 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 and here. So a total of 9 points that we want to look at in order to represent the integer pairs in this region. So in order to figure out what the slopes are at each of these 9 points, it might be helpful to first create a table. So at every ordered pair, I want to consider the t and the y, and then calculate dy dt. And on first sight, you see that this equation does not have t in it, which at first can be confusing, but if you simply write it as 2y plus 0t, the observation is that t simply does not contribute to the value of the slope. However, it is there, it's just invisible, and if it gets multiplied by 0, it does not really matter what the value of t is in this equation. So if I start off arbitrarily at the point 0, 0, in the ty plane, that's going to generate a 0 slope. Okay, well, a 0 slope is a horizontal line segment. So I'm not going to draw this horizontal line segment all the way across. I'm just going to draw a little tiny line segment here that has about a 0 slope and that points to the right, because of course we know time increases, does not decrease. Therefore we draw a directed arrow to the right with a slope of 0. So the incline of that little segment is 0. We would do the same thing at the other points, and let's go ahead and jump to the point 0, 1, which is this point here. When t is 0 but y is 1, dy dt is twice the y value, so 2 times 1 plus 0 times 0 is 2. And we can now generate a little slope segment at this point that has about a slope of 2. Now here would be, if it pointed right over here, that would have a slope of 1, but there's a point up here that it actually aims towards because it has a slope higher than 1, so I'm going to draw a little segment that looks like that. And I'm going to repeat this for 0, -1. And for 0, -1, if y is -1, then dy dt is going to be -2. So that's going to be similar to this slope vector except pointing downwards. And I'm going to continue this way. So we'll start off with 1, -1, and in that case dy dt will still be -2, which at this point here will have exactly the identical slope vector as we had just to the left of it. So keep in mind that the t value is not influencing where we are on the t-axis, does not influence the slope segment. We only are concerned with the value of y. So in fact, what we're going to see is that if you look at the t value of 1 and the y value of 1, that's going to be exactly identical to what we achieved up here, because as long as y is 1, dy dt is going to be 2. And so at the point 1, 1, I should probably be careful not to make those look negative. I'm just trying to illustrate that this point here and at this point here are going to have exactly the same slope. So at the point 1, 1, I'll have exactly the same slope that I had at 0, 1. And if I look at 1, 0, well, that's going to be the same thing as 0, 0. So I'll make a little symbol here, a little square, to show that these two will have exactly the same slope, because once again, the fact that t changed does not influence the outcome of the slope. And so this is going to have a slope of 0, and so we should see a horizontal line segment here. Now I'm not going to repeat this for the remaining 3 points, but we should see that if I maintain a y value of 0, I'll maintain a slope of 0. If I maintain a y value of 1, I'll maintain a slope of 2. And if I maintain a y value of negative 1, I'll maintain a slope of negative 2. So what we see is that these 4 slopes here, or these 3 slopes here, are the same. These 3 slopes here are the same, and these 3 slopes here are the same. But for any given value of t had no impact on that slope segment itself. So we kind of have these rows of vectors that look very, very similar. Well, what does this allow me to do, though? What did I gain here? One of the things I gained is a good visualization of what an initial condition is expected to do. So we don't have enough densely populated vectors here, but it sort of appears that any initial condition that starts off in the first quadrant, like that one, will somehow veer upwards. We don't exactly know how, but it looks like, and if we were to plot more vectors, these ones here would just be pointing upwards, but a little more steep. And if we start with an initial condition down here, it looks like that initial condition may end up veering downwards. So think about these as wind vectors. If you put a feather in the wind, these vectors kind of illustrate where that feather is expected to blow based upon where the wind is going. All right, so let's take a look at a little observation here. What can be said about the pattern for slope fields that are autonomous? That is, that only depend on the value of y. Well, what we should see is that the slope vectors are the same for a given value of y, independent, I can spell this, independent of the value of t. So what we kind of describe this as is we should have rows of similar vectors, I shouldn't even say similar, of identical vectors. Great. And one other thing that we see here is that we have also an equilibrium point. When y is 0, regardless of what the value of t is, if y is assigned to be a value of 0, then dy dt will always be 0. And so one other trajectory that we see here is that if you start off with a y value of 0, you will always have a y value of 0. And this would make sense in the context of things like populations, where you can't create animals out of a lack of animals. Let's also take a look at one that depends exclusively on t. This is something that we would have seen in our Calculus 1 class. And once again, let's just go ahead and look at these for t between 0 and 2 and y between negative 1 and 1. So once again, we're basically going to be looking at the slope at 9 different points. And I'm going to jump the gun a little bit here to observe this pattern, but as long as I'm maintaining the same value of t, regardless of what the value of y is, that should not change the slope. So I'm going to write this as 2t plus 0y. Again, for that purpose of seeing that the value, as long as t maintains a constant value. So when t is 0, that's these 3 points here. So 0, negative 1, 0, 0, 0, positive 1. all three of these ordered pairs, 2 times 0 will be 0, plus 0 times whatever y is, will still be 0. So we cannot call these equilibrium points because equilibrium points are the value of the dependent variable, but all three of these vectors would point horizontally. Now, when t becomes 1, and I look at 1, negative 1, 1, 0, and 1, 1, 2 times 1 is 2, so for all three of these points, we're going to have a slope of 2, which I'll just kind of draw like that. And then when t becomes 2, 2, negative 1, 2, 0, and 2, positive 1, 2 times 2 is going to be 4, so these are just going to have twice the incline of the slope. And I'm going to try my best here to just make it look more vertical, but hopefully you just get the idea that all three of these are the same. So once again, we see that these three are the same for that value of t. And when we change the value of t to 1, all three of those vectors are the same. When we change the value of t by 1, all three of those vectors are the same. And for an initial condition, one thing that we can observe is that it looks like, regardless of what the initial condition is here, it'll kind of start off a little flat and then start to pick up with more speed. Then anything below it will do pretty much exactly the same thing. And anything below that will do pretty much exactly the same thing. And so what we can think about these as is these are vertical shifts. So when you solve an equation like this, observe that we would get t squared plus c would be the solution, and that just emphasizes that every single initial condition will just be a shift of the same curve. Back up here, what we should notice is that within one region, like for example, when y is bigger than 0, all of these curves would behave exactly the same way, and they would all be sort of these horizontal shifts. So for that same initial value of y, but for a different t, we would just notice that all those curves are exactly the same. They're parallel, but they're, I shouldn't say parallel, but parallel-ish because of the fact that they are horizontal shifts. All right, we'll leave it at that. And so what can be said about the pattern here? Well, the slope vectors are the same for a given value of t, independent of the value of y. So in fact, I'm not going to even rewrite that. I can just copy and paste this, because copying and pasting is fun after all. And the slope vectors are the same for a given value of t, independent of the value of y. So here we notice we had columns of identical vectors. That is, we could circle one of these columns and see that all three of those behave identically.